These notes will tell you what you need to know about the spring force for AP Physics C. First, when we talk about the spring force, this is an example of a spring. Okay? If I stretch the spring or compress it, it applies a force at both ends. The spring force is the force applied by the spring to something else. It's not the force I put on it in order to stretch it, it's the force that the spring applies to something else. There's the symbol for it. Now the first thing to get straight is, if a spring is at its normal length like this, then the force it's applying is 0. Fs equals 0 when the spring is at its normal length. That's even if things are touching it. As long as it's at its normal length, it is applying no force. A compressed spring pushes, so if I go like this, the spring pushes back on me. If I go like this, the spring is pushing on the eraser and on my thumb. Okay? And a stretched spring pulls. So if I do this, the spring is stretched, it is pulling to your left on the pencil and pulling to your right on my fingers. In other words, what a spring tries to do, if you distort it, it tries to return to its normal length by applying a force at both ends to whatever it's touching. 99% of the springs in AP Physics C can be considered to be massless. They have no mass. And as a result of that, the spring force will be the same at both ends of the spring. That's really just the way to think of it for now. If there's an exceptional case, that would be an A question, and you can deal with that as it comes. Okay, so the way that we describe what a spring does, the typical spring follows a formula for how strong its force is. So first you imagine the spring being set down and connected at the left side to a wall, and now it's at its normal length. Since it is at its normal length, that means there's no spring force being applied, so Fs equals 0. We could call this normal length L, and there are problems once in a while where that would be considered L. Well, that would be important. You would name it L. And further, if you go into some kind of mechanical engineering, you will work a lot with springs. So you would deal with L. Now, the spring applies a force when its length is not L, when its length is not the normal L, and in fact, sometimes this would be called L0, the normal length of the spring. If we stretch the spring, then it pulls back. If we compress the spring, then it pushes. So the best symbol for this change in length would be delta L. That would be a very good symbol for this. It would be very explanatory. This would be a positive delta L because L is getting bigger, and this would be a negative delta L because L is getting smaller. Unfortunately, that is not the symbol that's chosen in most high school physics books and college first-year physics books. The typical symbol is X. So what you have to imagine, that X can be misleading because you want it to be the length of the spring. X is definitely not and never the length of the spring. What you imagine is that you've set the spring down and you mark one end of it, the end you're interested in, because that's where the force you're going to study is at this end. You mark that and you pretend there's a number line under the spring, and that place where the end of the spring is at normal length, when there's no force being applied, you label that, you define that as X equals 0. That's where you define, we can even put it 3 lines here. Define as X equals 0 right there, and then you have a number line under the spring. So remember, that's X equals 0, not over here. This is X equals 0. So if X is positive, the spring force pulls back on my fingers here and pulls to the left. If X is negative, like this, if X is negative, then the spring pushes to the right in the positive direction. That's something that's going to come up later, so let's repeat that. If X is positive in this picture, the spring force will be negative because it points left. If X is negative, okay, then the spring force is positive, it points to the right. What is X? X is the position of the end of the spring. Remember, X doesn't stand for distance, it stands for position. So X is the position of the end of the spring. And that position is 0 when the spring is at its rest length. Okay, now let's look down at this example. The spring has been stretched by an alligator. Right? So the spring has been pulled to the right. So that makes here's the position of the end of the spring. We call that X. And that is positive X. The spring force, in this case, would point which way? Well, of course, the spring is pulling this way on the alligator's tooth. So the spring is pulling to the left, when x is positive, when the position of the spring is to the right or stretching the spring to the right of 0. Okay, there's a formula for this. If x gets bigger, let's just think not in terms of a formula, but just let's think in terms of common sense. For small x, you get a small pulling force, and for a bigger x, you get a bigger pulling force. Right? So the formula for the spring force should depend on x, and as x gets bigger in absolute value, that spring force should get bigger. Okay, so it's not a constant force like the force of gravity is over short distances near Earth. It is a force that depends on position. And that's one of the reasons we study it in this chapter. And since the force depends on position, we can graph the spring force. We can graph the spring force versus position. All right, let's look at that graph. First, I will show you the graph as if you were a mechanical engineer and you wanted to know it accurately and all the details, and then I'll give you the simplification we use in AP Physics. All right, so at first, when you first start applying a force to a spring, it doesn't move very far. A typical spring has a certain region here where you apply force, but the x does not increase. If you pull on a spring, it doesn't move very much. And then you get this very linear behavior like this. And then after a while, if you start to stretch the spring too much, what happens if you stretch a spring too much? Obviously, I'm not going to do it here, but if you stretch a spring too much, you start to distort it. And the curve starts to go like this, and then eventually, what happens if you stretch it so much you get a straight wire and then pull hard enough, you get a break. So this is called the breaking point. In this region here, this is where we want the spring to operate inside a machine. This is called the linear region. That's from here to here. This is the region where the spring becomes deformed, where we're actually reshaping the spring in a way that makes it is permanent, and it cannot be restored to normal unless you melt it down and recast it. The word for this region comes from a Greek word for to mold or shape something, which is plodsto, and that's where we get the word plastic. So this is called the plastic region. This does not mean the spring suddenly turns from metal into plastic, not at all. This is a different use of the word plastic. If you're at all familiar with the arts, the plastic arts are the arts where you mold things, like sculpture, pottery. Those are the plastic arts. So plastic is from a Greek word to mold. So in this region, we never want to use the spring in this region because we basically distorted it and it's not going to work properly. And then this early region here, where the spring follows a curve, this is called the nonlinear region. Now, if you want a spring to behave in a predictable way, and for use in a machine, you would use it in the linear region. So, if you look at this linear region and extrapolate it and see what would the equation of this curve be here? Well, obviously, it's linear, so it'd be like y equals mx, but it's traditional to use a k, y equals kx, but it does not go through the origin, so technically it should be y equals kx plus b. But we follow a simpler model in AP Physics, and in fact, in any kind of first-year physics class, you follow a simpler model than f equals kx plus b for this region. If you go into mechanical engineering, you would look at this more accurately and come up with a better curve for it, a better equation for it. And in fact, if it's not perfectly linear, you might add an x squared term or a square root of x term, more terms to make it more accurate. But in AP Physics, we don't even use this. This is too complicated for us. So we use the model Fs equals, you want to put a gap here and then write Kx. So in our model, B is very, very small. So small that we ignore it. And in fact, I have springs like that. Like this is a spring that behaves pretty well with the B for this spring is just about 0. But I have other springs with a significant B. Now, remember from the previous page that if x was positive, the force pointed in the negative direction. And if x is negative over here, the force points in the positive direction. And for that reason, you put a little negative here. I like to put that negative in parentheses. If you put arrows above these, it's a true negative. I like to put it in parentheses. It's a reminder. So this is giving us a relationship between magnitudes. The strength of the spring force is a constant times the stretch or compression of the spring. And the negative is to remind me that it points in the opposite direction. You'll probably almost never use that negative when you actually do problems. Okay, let's look at this thing here, K. K. First, the unit for K, since X is meters and force is newtons, the unit has to be newtons per meter. And 2, would it be the same for all springs, like capital G is the same everywhere, or would it be different for different springs? Would all springs have exactly this slope here, the same relationship between stretch and force? No, of course not. This spring is pretty easy for me to compress and stretch. Okay? This one is not too bad. Okay, I can compress that without too much trouble. And then this spring here, I'm going to push as hard as I can. 2 hands. All right, almost doesn't compress. So this spring has a big K. So bigger K, stronger spring. K is a measure of how strong the spring is, of how many newtons you have to apply to get it to stretch 1 meter. So if a K, for example, a typical spring in the lab like this one has a K of about 15, that means you have to apply 15 newtons to get it to stretch 1 meter. This one actually feels like less than 15. I'd say maybe it's less than 10. And a big K means you have to apply a lot of newtons to get it to stretch 1 meter. And finally, this K can be called the force constant, which is a little general, but it can also be called the spring constant of the spring. It can be called the force constant of the spring. I like to call it the spring constant. And when you buy, let's say you go into mechanical engineering and you're devising some machine, and you figure out what kind of spring you need, you can open up a spring catalog, and they have all sorts, and you decide by diameter, by length, and especially by K. And you order the spring that you want based on the K that you need for the job.